Our third question on our buffered worksheet reads, a buffer is prepared by adding 5 grams of ammonia and 20 grams of ammonium chloride to produce enough water to form 2.5 liters. We'd like to know the pH of our solution. So, knowing that, we'll need the Henderson-Hasselbalch, that pH is equal to pKa plus the log of the ratio of base over acid. We have some molarity work to do. We begin with 20 grams of ammonium chloride, NH4Cl, and we also have 5 grams of ammonia. Ammonia, of course, would be working for molarity of base, and ammonium chloride is going to give us its conjugate acid, the ammonium ion. So the conjugate pair in this buffered system is ammonia and its conjugate acid, ammonium. We'll do some molarity calculation by taking grams over molar mass over liters to find big M molar solution. So I'll hit for the molar mass first of ammonium chloride. 14 for the nitrogen, 4 more on the hydrogen, and 35.5 for the nitrogen, or the chlorine, and I get 53.5 grams as its molar mass. Let's also just place that over the volume of solution, 2.5. So hitting for the molarity of ammonium chloride, I hit my 20 grams, divided by my molar mass of 53.5, divided by 2.5 liter units, and my screen reads 0.1495. Let's make that 0.15 molar solution. On to the work for the base. 5 grams over the molar mass of 17 for ammonia per 2.5 litered solution. And calculating its molarity, 5 divided by 17 divided by 2.5 liters, and I have 0.1176. Let's make that 0.118 molar for the base. pH can be found by taking the pKa plus the log of the ratio of base over acid. However, this conjugate system using ammonia has a Kb value. Using the Appendix D for ammonia, it actually is listed in the small table for the Kb values, first in the list, as 1.8 times 10 to the negative fifth. But when I use Henderson-Hasselbalch, I must have a pKa value, so I'll let the calculator convert for me. Using the ion product constant for water, 1 times 10 to the negative 14th, dividing out the Kb value of 1.8 times 10 to the negative 5th, changes the Kb into the Ka. So pKa of the system is negative log Kw over Kb, plus the log of the ratio of base over acid. The base here is ammonia. Its concentration was determined to be 0.118 molar. Set over its conjugate acid that came from the ammonium chloride solution, 0.15 molar. So here we go, clear screen. We'll hit negative log of the ratio of Kw divided by Kb. Negative log of 1e negative 14 divided by 1.8 e negative 5, plus the log of the ratio of 0.118 divided by 0.15 base over acid, and we get a pH reading of 9.15 pH units. That number makes sense. This is a base, ammonia, so therefore it should end up with a pH greater than 7, and this does, so the number makes sense. It is a buffered solution, so in letter B, it's asking us to consider a net ionic equation, or a complete ionic equation, for the reaction that occurs when a few drops of strong acid, such as nitric acid, are added to the buffer. Remember the conjugate pair of ammonia and the ammonium ion. This is our buffered pair of conjugates. If I add a strong acid to a buffered solution, an acid will react with the base. Considering what we're showing, nitric acid is HNO3. It must react with the base from the conjugate pair, ammonia. Alrighty. Now, eliminate the nitrate ion and simply show the acid as the proton H+. Nitrate is a spectator and is just simply thinking about the net ionic equation. When hydrogen ion, the source coming from the strong acid, reacts with a base from our buffered system, we transfer the proton and simply produce NH4+, the ammonium ion. So in this particular equation, H+ added onto the base, NH3, we know that addition of strong acid produces more of the conjugate acid and consumes the base from the buffered system. And in the letter C, what happens to the buffered system when we add a strong base, such as potassium hydroxide, to the buffer? And again, if the buffered partnership is ammonia and its conjugate acid ammonium, potassium hydroxide is a strong base. A base reacts with the acid in the conjugate buffered system. So let's consume hydroxide with the ammonium polyatomic ion. The base reacts with the acid from our buffered pair. Again, think proton transfer. We will produce ammonia and a water molecule. The proton transfers from the acid to the base. Acids are proton donors, bases are proton acceptors. So we form more base when we add a strong base.